Hello, and welcome to a different sort of video. I've been doing some image processing lately in Matlab, and I identified a gap in the knowledge, primarily because Matlab's documentation and all the documentation out there seems to relate to the specific algorithms and functions that Matlab has built in. But you don't really get to understand these algorithms and how they work on a fundamental level per pixel until you write an algorithm like it yourself. And so this is the first in a set of videos that I plan to make, which will start from finding the neighbor of a certain pixel in an image, and then we'll step by step lead that up into region grouping and image segmentation. So if you're struggling with any of those types of things, watch these videos. I'll walk you through the algorithms step by step. So let's get to it. Now firstly, this is the image we're going to be working on. Now as you can see, it's a grayscale image. It's got a 3x3 grid of differing mushrooms at different grey levels inside a different grey level square. So this will be very easy for us to segment because we can set an initial pixel, for example one that's right here, find all its neighbours, and then eventually find this region excluding the mushroom inside. Now the way we're going to do this is by using a thing called a threshold value. So by doing a threshold value, we can severely dampen the noise between these two regions. So in typical images, there's one color, then there's a gradient, between a hard another color. So between these two sections, there is actually probably, 5 or 6 pixels which have differing gray levels, which gradually transitions from one to the other. And so with the threshold value, we'll be able to notice for very small threshold values, it won't pick up every detail. But as we increase the threshold, it will begin to harden these lines. And at a certain point, we might transition where our region, including our threshold, encapsulates the entire square, including the mushroom, because, for example, this one, or this one, the grey levels are kind of similar. So if we put a threshold value quite high, the difference between this grey level and this grey level might actually be within that threshold, and thus our region that we group and segment may include both the mushroom and the background. But for now, we're just going to focus on finding the neighbours of a particular pixel. So let's get to that. Alright, so I've initially jumped the gun here. I've created a new function in our directory called Neighbours. Inside that function, I've defined that we will be returning the x and y coordinates of the neighbours of an input pixel. Into this function, we will take an 8-bit grayscale image, which we will pass it our mushroom photo. We will take the coordinates of the initial pixel we want to check to see if it has any neighbours, and a threshold value. Now to start off, we want to define what a neighbour is. Now jumping over to this image, we can define what a neighbour is. So there are two outcomes of what a neighbour can be. We can use 4 neighbours or 8 neighbours. Now 4 neighbours is if we have a pixel P. The 4 neighbours are the 4 cardinal directions: up, down, left, and right. These are the 4 neighbours. Now we can have 8 neighbours, which also incorporates these 4 corners. So as well as these 4 here, it has the 4 corners, which means a surrounding pixel P, all of these are 8 neighbours. Now for a binary image, a neighbour is if, for example, if pixel P is 1, any of these pixels that are 1 would be classified as one of the 8 neighbours of P. But for this example, we're just going to deal with 4 neighbours, and along the way I'll describe what we can do if we want to use 8 neighbours. But for now, we're using this, up, down, left and right. So the coordinates of P, we want to use the x minus 1, the y minus 1, the x plus 1, and the y plus 1 values. So to do that, firstly, we're passing in an image. So it's always good when you're dealing with values to just make them doubles. Give yourself as much precision as you can. So now we've taken this image, we've made it a double. We want to take the x and y coordinate. So taking our input, we want to check these 4 coordinates. So how are we going to do that? And the best way we can do that is by using a convolution. So we want to define the uppermost pixel as the image convolved, and this is the Matlab convolution. We want to use we want to have pixel. We want to. So what I'm doing here is defining a mask. Now the mask is going to go around here. We're going to make one for each of these. So the rest of the values will be 0, and this one will be 1. And only when it's 1 will it read in the pixel value and tell us, which we can use to then check if it's within a threshold value. So we're creating an zeros array, and what we want to do is we want to size of image. So now pixel will make a zeros array of the size of our original input image. So for that, we want to then go pixel and create a mask. So for this, we're using the uppermost, we're checking this pixel here. So what we want to do is we want to make this value 0, 0, 0, 0, 0, 0, 0, 0, and this one be 1. Now in Matlab, we do 0, 1, 0, 0, 0, 0, 0, 0, 0. So that is convolving to check. We want to make sure it's the same. And if you need to classify, confirm whilst this works, you can search up to Matlab or type help convolve to, and it gives you all the information here. You can go ahead and read that. But this essentially is a mask, and it's going to take the pixel we want, convolve it with the mask, and return the value that's in the uppermost position. So then we can do that for all of ours. Okay, so that's checking the up value, because this is the value that we're taking in. This is the pixel of interest, so we're checking the pixel above it, below it, to the left, and to the right. So now that we'll be able to return that information, we want to actually check that it's within our given threshold value. So the way that we do this is we want to take the absolute value of the value in the up position minus the pixel of interest. So now for the pixel of interest, we want enter s. equals the value of the 8-bit intensity of the image at x0, y0. So if you just want to confirm why that works, so we're looking into the image at the coordinates of x0, y0, and that's going to be the intensity of our pixel of interest. So now we're taking the absolute value between the difference between the value in the up position and the pixel of interest. So the difference between the value here and the value here in our image. We want to check that that is less than or equal to our threshold value. And if it is, so I'll just make that if, and so if this is true, then we want to define, so I'll store these in a temporary array. Let's call them xtemp equals open array, ytemp equals open array. Actually, no, I'll just call them x and y. So, if that is true, and we want to check if so this is a caveat for why this will work, but checking if this value is empty, if it's not equal to 1. So what this will do is on the edges of our image. So if we open up our image again, the edges, here, 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 here. This is the primary reason why using the convolution method is a lot nicer. So if you were just to say, read in x, y values and then do the hard coding. So simply hard code these values in. Simply hard code these values in, that if it's within the threshold, then this is the equation. Then when you're at the edges, and specifically when you're at the four corners of the image, those logical if statements break down. So it's really difficult to build. You'll have to build special cases for each of the four corners plus each of the four edges. So that's 8 special cases that you have to write if statements for, as well as all the if statements for the 4 neighbours. And if you're doing 8 neighbours, it's even more. So what this does is if it's on the edge or a corner, it just returns an empty array. So what you're checking here is if it's empty. If it's not empty, to be specific, that's when we define the first position of x equals x0, and the first position of y equals y0 minus 1. Because that's what we see here. Yep, we're going x equals the same x value as the input pixel p, and the y value is the y value for pixel p minus 1. So that's what we're doing. And then we just repeat this for all 4 cases, just changing these to match up with these. So let's do that now. Alright, so let's see how this works. We want to save, and then we want to first define our image. As our mushroom image. So it's appeared, it's 1000 pixels by 1000 pixels. We want to then call xy equals neighbours. We want to pass our image, our initial coordinates, which we'll just call 50, 50. I don't know where that is in the image, but we'll see. Let's go a threshold of 1 and let that run. So there are no neighbours within 1 pixel. So let's open this, go to 50, 50. So why hasn't that worked? Because obviously this pixel, this pixel, this pixel, this pixel are all within 1 value. So why hasn't that worked? Oh, okay, I forgot. I was convolving this with, we want to go pixel at the x0, y0 point equal 1. So we're convolving this with a 1 that's here. So that should work now. There we go. So we have the 4 coordinates. Let's go down to 50. Go across to 50. Right here. So the first coordinate is an x value of 50. Yep. With a y value of 49. So 50, 49, 50, 49 I should say. And we want 50, 51, 50, 49, and 51, 50. There we are. So here are the 4 pixels. There, 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 and there. With all the coordinates, 50, 49, 50, 49, 50, 51, 49, 50, and 51, 50. Because Matlab goes row, then column. So that works. Now we want to check for edge cases. So if we go over here, let's go row 6, column 1. We should change that to 2. We want that one, we want that one, and we want to see if it only returns these 2 neighbours. Let's do that. So we want 1, 8. So now this is an issue. This is exactly why I did this test. So this is the pixel of interest. Oh, did I do 8 one? But I wanted to do 6. There we go, sorry. 6 1. So we got 7 1 and 6 2. But what we don't have, instead we have zeros here and to the left, which would be here. So what we want is we want to remove the zeros out of this array. So the way we do that is just before we finish the function, we go x equals x does not equal 0. Y does not equal that. And let's run the same thing again. And there we go, the zeros have gone. So that is how we find the 4 neighbours of a pixel in a particular image. I will see you in the next video where we will talk about connected sets and how you can formulate a set of pixels, also known as a list of all the x and y. And I'll give you a hint. What we will do is recursively check the neighbours that we find, and that way we'll pick a pixel, find the neighbouring pixels of that initial pixel, and then we will find the neighbours of those pixels, and so on, until we have a selected region. Until then, I'll see you in the next video. I hope you learned something.